Okay, welcome to the third of the gas processing tutorials. In tutorial 2, what we did was to build a simple steady-state OLGA case. What we'll be doing in tutorial 3 is to tweak that case that we built in tutorial 2 slightly, and then what we'll do is to actually expand this to be a multiple well case. So you can see here that we have our case from tutorial 2, and the first thing that we're going to do is to just quickly show you how to duplicate a case. So what we can do instead of starting from scratch every single time is just go up to this little button here which says duplicate case. You can click on that and you can see it brings up a little window where we can name our new case. This is going to be tutorial 3 start. There we go. Yes, we wish to do this. Okay, so as you can see, this has created a new case up the top here. This is tutorial 3 start. And what this means is that if we break anything in this particular case, we can always just go back to our tutorial 2 by clicking the tab up the top here, and we know that this particular case is going to be working. So the first thing I'd like to show you briefly is what happens when you change the names of various different things within the OLGA file itself. So we have our material here. Let's just fix the spelling on that. We have a steel pipeline. And when we did that, what you should notice is that now we have this situation down here where the simulation is not runnable. So if we click on our little verify simulation up the top here, this tells us that in exposed pipe, the reference for material type is wrong. So if we click on that, or alternatively, if we just click on our wall here, our exposed pipe, we can see that this material type is no longer valid. So what we would have to do is to remove the old one and replace the new name in here. Now you can see that if you were to change or add, for example, a new wall material, you would then have to go into your various different flow components and your piping, and you would have to change the wall for each and every single one of these. So what we're going to do in this tutorial then is to firstly look at changing the way the boundary condition is handled. So at our inlet here, we currently have a mass flow source, and what we're going to try and do is to replace that with a pressure source. We'll do that by putting in a pressure node similar to the separator node that we have up here. Before we go changing anything, let's just see how the system performs without any of these changes. So if this is a mass flow specification here, what we're going to do is to try and have a look at how mass actually flows through the system at the present time. And we can do that by taking a look at the outputs from the well bore. And we can take a look at the different variables that we're actually going to be tracking to begin with. So if we click on this, you can see that what I've actually already gone and done is to select the mass flow rate of oil and the total mass flow rate of water, including vapor. So the way that we found this was to search in the little description box here for mass flow rate. And what we can do when we're doing these searches is to actually sort them by these different types. So we can look at, for example, sort by group, and you can see that these are basic conditions where our mass flow rates belong. So what we can also do, instead of looking directly at the mass flow rate, we can look at, for example, volume flow. And you can see we have, in this case, you can see a gas volume flow. You will see an overall liquid volume flow. There'll also be various volumetric flow rates for oil and for water. And if you have the volumetric flow rate, you can then also look for the density, oil density, gas density, and water density. And if you just take those two values together, then you can manually calculate a mass flow rate. Now, you can also use this as a cross-check of the two different methods to see that they are consistent. So in our case, we'll just be using the overall mass flow rates here and here. So if we choose to track those two values in the well bore, then what we do is we go ahead and we run our simulation. And I'll just put a brief cut in here while we wait for that to finish up. Okay, so our OLGA simulation is finished up. And we can just tap enter. And now what we can do is to just take a look at what that mass flow rate actually looks like. So when we click that button, it brings up our little select variables window. Again, we're interested in looking at the well bore, so we can filter out for the well bore specifically. Now let's take a look at the mass flow rates. And let's also take a look at the pressure here. Okay. So now what we can see is that there was a mass flow rate specification in this source of 20 kilos per second. And if we add these two mass flow rates, then that comes out to be about 20 kilos per second. So that seems to be holding up that specification quite nicely. What you should also notice about this is that it is slightly different to the way that we had our original picture specified. So if we just change the units here by going right click, edit, select, and in this menu, if we just click on the right hand side of our units, we can switch that to PSIA, go OK, and you can see this is updated. So in that original picture that we had of this system, we thought that we would have an inlet pressure of about 1300, but you can see that that just isn't the case here. It's actually somewhere above 1800. So we can say view, track values. There we go, 1843 at this inlet. And so we have to ask ourselves, why is this happening? And the reason comes back to the way that we've specified our OLGA simulation. So we've given our outlet separator our pressure boundary condition of 300 psi, but instead of telling the simulation that we have a 1300 psi inlet, what we've done instead is to say that you are pushing 20 kilos per second of mass through this system. And what OLGA has to do then is to work out what pressure drop is required across this system in order to push that much mass through. So what it does is to basically back calculate that it needs a pressure somewhere around the region 1850 to 1900 psi in order to drive this mass flow rate. So what this does then is sets up an ability for us to change the way that this system is specified and to replace this mass flow rate specification with simply an inlet pressure node. So what we're going to go ahead and do now is to delete our source and to delete our wellhead. So we're going to chuck in a pressure node. This pressure node is going to be called a well. There we go. Sometimes we have to do this a couple of times. Alright, so that's going to be our well. What conditions does it have? Well, our reservoir was at 200 Fahrenheit. Our pressure, let's try 1840 psi. And our fluid is our black oil. Last thing we should have to do then is to connect our original wellbore to our well. There we go. Now it says not runnable, but when we press verify, note that that says ready to simulate. Okay, so let's go ahead and try to simulate this. We'll run batch and we will see what happens. Okay, so the first thing to note is that immediately when the OLGA command window popped up, it says, warning, the steady state processor did not converge. So if you remember from previous tutorials, basically when OLGA is running a case, what it does to begin with is to just quickly run a once through steady state calculation in order to get some idea of the initial values. Now what it's telling us in this case is that that did not converge properly. And again, when we come to the end, it says normal stop in execution, but the steady state processor did not converge. So we can press the any key to continue. And one thing that you should really note about those sorts of errors is it doesn't necessarily mean that you've specified something incorrectly. But what we can do is to check the actual results and see if they then make sense. So let's go back to our profile plot here. And what we can do is to just press this little reload button in order to update plots that we've created previously. So if we press that, we'll note that our mass flow rate and our mass flow rate is now defined from the inlet because we've actually defined this boundary condition as being the source of the flow rather than the flow injecting in partway down the line. So what we should do is to just advance this forward, and we can see immediately that something interesting happens as we go along here. So what we can see in this case is we have pressure decreasing from left to right as you would expect, but we have backflow in this situation. Now that's very interesting, and it basically comes down to the idea of static head. So what this simulation is now telling us instead is that despite the fact that we have that same specification, more or less, of 1840 psi at the inlet, that isn't actually enough to drive that 10 kilos per second And in fact, the static head is such that we're getting backflow through our inlet condition here. So what this means in practice is that if we want to get forwards flow and actually produce some oil, then we have to bump up the pressure that we have available at the inlet. And so this is just sort of a lesson in the requirements of static head to actually get this thing to work properly. Let's change our inlet pressure up to 2000 psi, and we'll run that case once more. Now the first thing that we can note in this case, there is no error message about the steady state processor. And we'll pause this and come back to it once it's finished. Okay, so now we have a normal stop in execution. There are no error messages below that. We just press any key to continue. Now let's go back to our profile plot again and refresh. Okay, so if we run through this, we can see that it's stable, more or less, once we get to this end point here. And we can see that we now have forwards flow. We also have rather a lot more flow than we were anticipating originally. And the reason for that is just that we have that extra 100 psi or so pushing the fluid through here. So that extra 150 psi that we added, that was enough to firstly overcome the static head, and secondly then push this much mass through the system. So what we're going to do now is to take a look at how we can add a second well into the system. So basically when you're building these sorts of simulations, what you should always do to start with is to try and solve a number of simple cases. And then you should add in layers of complexity very slowly and make sure that each of these individual components actually works before you do anything more complicated. So what we're going to be doing first off is deciding where it is that we want to connect in our second line. So what we're going to do is to put it in at the riser base here. In order to make things a little bit simpler, let's change the name. So this is going to be well A, well bore A, well head A, and flow line A. Okay. And then the riser base is where we're going to connect these things together. So, if we want to connect our system at the riser base, then what we should really be after is a similar pressure coming in from both sides. So, what we can do is to create a new profile plot, this time of the flow line itself, and we'll be interested in looking at our pressure primarily. Okay, so again we can change the units to psi. There we go, and we can see that our outlet pressure here, that's 431 psi or so. So that's the sort of outlet that we're going to be expecting from our second reservoir, or our well B. So the way we're going to do that is to just select a whole bunch of this stuff, Control C, Control V, and you can see it creates copies for us. So you can see that again the simulation is not runnable, and that's because we now no longer have an outlet for our second flow path in here. So what we'll do is to just rename these things. So this is well B, well bore B, well head B, and our flow line B. So, as I said, the best thing to do is to actually solve these individually before you go ahead and connect them. So, what we're going to do is to chuck in a pressure node here, connect the outlet from our flow line B. Let's call this our riser base check. And what we want this to do is to act as a proxy for the conditions at this riser base here. So what we need to do is to chuck in a temperature. Well, that's going to be the same as the seafloor temperature, about 40 Fahrenheit. We're going to need to chuck in a pressure, which is going to be our 431 psi, and the fluid, for the moment, we'll just stick with everything from Reservoir A and see if this goes ahead and runs. So again, verified, simulation is ready to run. Let's run that batch, and we'll come back to it once the simulation has actually run. Okay, so we can again see normal stop and execution. Now I should note that that took, well, roughly double the amount of time to run as the previous case had. And that's just because we've doubled the amount of stuff that's actually in this simulation. So what we can go ahead and do is to create yet another profile plot. And what we'd expect to see in this particular case then is that flow lines A and B are going to behave in a fairly similar way. So let's take a look at the pressure, temperature, and our flow rate. So we create this plot, and you can see that these curves lie more or less on top of each other. So this sort of similarity is fairly encouraging. It seems to suggest that things have gone well in our copy-paste process. And what we can do now is to actually begin to modify this second section of simulation here in order to better represent our reservoir B. So the first thing that we need to do is to actually create a fluid B. So what we're going to have to do for that is to go into Multi-Flash and open up our OLGA tutorial, and we'll take our original black well with water case. We'll open that, and what we're going to do is to just tinker with the composition slightly. So let's roughly double some of these components. We'll set our this to 9. Let's have 6 moles of this, 5 and 4. And finally, let's reduce the amount of water that's going to be in this second reservoir here. So, how is this going to change the fluid? Well, the easiest thing that you could have done was to just create a phase envelope, and then change the composition, create a new phase envelope, and see what those differences actually are. Now in this case, we haven't made any huge change, so the differences should be minor. The major change is actually that we've reduced the amount of water in the system, and that's going to have much more of a major impact once we start considering, for example, hydrate formation, and I believe that will be in tutorial 5. Okay, so what we can do here is to save this as a separate problem. So rather than black well with water, this is going to be Reservoir B. We will save this MFL file. We now also have to create a new OLGA tab file. So let's click Browse. Let's say this is going to be Reservoir B. Open that. And the fluid ID is Reservoir B. There we go. And again, we need our table conditions. Let's once again have our pressure going from 100 psi. This time we're going to take it up quite a bit higher. So let's just say that we want our reservoir pressure for Reservoir B to be about 3000 psi. Let's take the table up to 4000 psi. Our temperature, once again, -10 we'll use here, and let's say 300 Fahrenheit. Now our standard 50 points for each of these, and we'll calculate the table. There we go. Okay, so reservoir B.tab has been created. So we can go ahead and put this to the side for now. Let's go back to OLGA. Now what we have to do here, as we've just created a new fluid, is to take a look in our case definition, files, and our PVT file. What we can actually do is to add in a second PVT file. So we can see here, Reservoir B tab, open that, and now we have both of them available within the simulation. So what we want to do is to change over the fluid in section B to be using our new Reservoir B fluid. So there are a few different places this has to change, at our nodes and along the flow lines themselves. So at well B itself, you can see we now have Reservoir B in here. At wellhead B, we need to change this, and in the riser base. Now similarly, on our flow paths, we have well bore B, piping, and under branch, we set Reservoir B, and also for flow line B, piping branch, there we go, Reservoir B. So we should have our fluid B set up along the entire pipeline. Note that we're still using the original bathymetry, or the original geometry that we had with A. But, as we've changed something, we may as well just run a new case and see if it works. Now before we do this seems as good a time as any to save our case. So what we're going to go ahead and do is to again duplicate this. Let's say tutorial 3, multiple wells. Okay, so we can see we're now in our tutorial 3, multiple wells up here. Okay, so we've set up our well B with our Reservoir B fluid in it. But what we wanted to do with this particular reservoir was to have a higher pressure at the inlet. So let's set that to 3000 psi, run our case, and if we drag the window over here, there don't seem to be any immediate errors, so we'll just leave this until it's finished. Okay, so we have a normal stop in execution. And now what we can go ahead and do is to create new profile plots for our flow lines A and B. And what we should see is that these behave slightly differently now. So flow line B pressure, flow line A pressure, and let's take a look at those flow rates as well. Okay, so let's just uncheck these flow rates to begin with. And you can see that for flow line B, we have significantly more pressure being used to push through the system. Now what that should mean is that our liquid flow rates for B, much higher here, but what about our gas flow rate? Interestingly, for flow line A, it's actually a little bit higher to start with. Now, we bring our pressures back into this. Part of this is going to be due to the fact that given the pressure is simply so much higher for well B, the density is also going to be a lot higher. So you're potentially going to be cramming a lot more mass into that same volume. So the actual mass flow rate for B may be higher, despite the fact that the volumetric flow rate is a little bit lower. Now onto the final stage of our edits and changes to flow line B. What we're going to do is to change the geometry very slightly. So if we double click on our wellbore B, what we are going to do is to increase the depth of this well. There we go. Let's change that to 5880 feet. That is a little bit extra static head that it'll have to push along. And secondly, what we're going to do is to go ahead and change flow line B as well. So, once again, let's change these to looking at it in feet. Now, what you can actually do in OLGA is add multiple pipe segments, one after the other, if you want to do some interesting things with the bathymetry. So, if we just right-click on pipe 1 and press insert after, you can see in this case it's just added a direct duplicate. And if we go back into our geometry view, you can see it's added this new chunk pipe along here. Now, what we're going to do is to slightly increase the length of the flow line and slightly change the elevation. And what we're also going to do is add in 5 sections here. Now we're going to add in some more of our pipeline. And we're going to bring this back down to 50 feet. Again, 5 sections. And we'll have one final section of pipeline, which gently rises to 60 feet. And we'll do that in 10 sections. Now, if we go back to our geometry tab here, which actually displays things for us, what we see here is that this was basically the geometry of flow line 1, and we've added this extra little feature to the end of that. So we've extended the flow line slightly, and we've changed, or we've added in a hill here. So we can close that, we can save it, yes. Okay, and this says not runnable. Well, why is that? If we take a look at our verify button, we can see there are actually 2 things here. So pipe 1 is apparently now incomplete. So you can see this is in well bore B, pipe 1. Now when we change that, what actually happens is it resets the number of segments. So we can either change that within the geometry itself, or we can just chuck in 10 segments right here, and we'll see that problem goes away. Now secondly, we have a number of different errors relating to this heat transfer module. So you can see the way that flow line B's heat transfer module is now defined. This is flow line B heat transfer is only defined for pipe 1. But if we click on this, we now have pipes 2, 3, and 4 within this entire flow line. So what we can do is to just transfer all of this over and say OK. Now, potentially what you can do is to make that a little bit more complicated, depending on your particular system, But for our cases, we're just going to say that this is at a constant ambient temperature of 40 Fahrenheit. Alright, there's one final thing that we want to do, and that's to track the mass flow rate in flow line A and in flow line B. And we'll see why in just a moment. But what we'll do is to go to our profile data, and we'll look for mass flow rate, sort by basic, and we want the mass flow rate of oil, and we want the total mass flow rate of water, including vapor. Okay? And similarly for flow line A, we will add these variables in. Now, once again, you can also do this by taking a look at volumetric flow rates and their densities and calculating it manually. Okay? Now we're tracking these variables that we're interested in, and again, we'll go ahead and run a simulation. Okay, so again, we can see here steady state preprocessor did not converge. That is slightly concerning. Let's take a look at our profile plots. In fact, let's create a new profile plot. This time, we will be looking at our flow lines, and let's take a look at the mass flow rates in A, B, and also their pressures here and here. Those both in PSI. Okay. Alright. This doesn't seem unreasonable. What can we note from this? Well, from our pressure plots here, you can see at the end point of each of these pipelines, they've wound up at this specification that we wanted them to be at. You can see that despite the extra length in the hill and the extra depth of the wellbore, the 1000 psi pressure drop that we gave to well B more than overcomes these factors. So the mass flow rates for B are much higher than for A. Now, this is going to be very important for the final section of this tutorial where we actually connect everything together. So, when we go ahead, and in fact, before we go ahead and connect everything together, let us once again duplicate our case. And this can be multiple wells before blending. Okay. What we're basically going to do now is to delete our pressure node here and connect the outlet of flow line B to our riser base. Now, the interesting thing about this now is we have to think about what fluids are being defined and where. So you can see it makes sense in well B to have reservoir B, or our reservoir B fluid, in well A to have our original reservoir A fluid. But what about in the riser base onwards, where these things blend together? And the answer really comes from that previous profile plot that we had here. What we're going to have to do now is to use this information on mass flow rate along with multiflash to generate yet another set of tab files. So, if we bring up multiflash once again, this was our reservoir B that we looked at previously, and what we're going to do is to blend our fluids together. And so what we do is to go Tools, Blend Fluids, and you can see number 1 here, this is our current specifications, this is fluid B. We can browse to our black oil with water, which was our reservoir A, and we can open this. And we can see here that one of the ways that we can blend these things together is to look at these fluid amounts. And you can see from the drop-down that we have kilos and we have kilos. So the way that we're going to get our mass flow rates is to once again go back to our profile plot, and we can right-click, view our track values, and we can see that at the end of the flow line here for B, we have about 66 kilos per second in our total mass flow rate. And for A, it is roughly 27. So what we do is to go back into multiflash, and we say that, well, per unit time, we're going to have 66 kilos of fluid B and 27 of fluid A. Now what we can do is to press OK, and we'll be asked, do we want to overwrite the current fluid? Yes, we do. Now the important thing here is that the first thing we do is we save problem setup as Reservoir B blended. So what this does is to not overwrite our previous multi-flash files. So now what we need to do is to create that new OLGA tab file. And once again, we can say AB blended. And our fluid ID is going to be AB blend. Now for our boundaries. Now we would expect that given our two fluids are supposed to blend around 400 psi, we wouldn't expect a huge amount of pressure is required here. But bear in mind that OLGA is a transient tool, so during those transient episodes you can see some interesting things happen. So we're going to give ourselves a lot of leeway in terms of our finishing point for the table. Again, 50 points for each. We'll calculate our table, and you can see that actually our models and phases are not defined. And the reason for that is that when you blend fluids, it actually resets all of your model parameters. So what we have to do again is select PR Advanced. Let's select Peterson here. Let's use mixing rules for our thermal conductivity and surface tension, and make sure that our phases are set up properly. So now our models are defined. Let's go back to table, OLGA, our settings are remembered in here, calculate table, and we can see now we have our blended fluid in here. So now we can go to OLGA. Once again, in our for blending here, we can take a look at our case definition, our files, and we can add our new tab file, which is AB blended. We can open that and press OK. Now what we want to do is to change the type of fluid in this last section of pipe here. So we'll change that to AB blend, we'll change our separator to AB blend, and in our riser we will change our branch fluid to AB blend. So once again, everything is verified, and we can go ahead and run the simulation. Okay, once again we finished. Steady state preprocessor did not converge. Okay, so let's just see what our results look like. Profile plot. Let us take a look at the pressures in flow line B and flow line A. We can change our pressures to PSI. There we go, okay. Alright, and what we can see here is that they start off at some different value, that's fine. But when we get to our endpoints of each of these pipelines, we have the same pressure. And that's what we were expecting to see, because when these things blend together and then go up the riser, we expect them to be at about the same pressure so that we don't have any sort of issues with backflow. Okay, and if we advance time, we can see that, yep, that seems to be more or less consistent. So if our pressures look okay, what about our mass flow rates? So we again edit select, and we can add our mass flow rates in flow lines A and flow line B. Press OK. And how does this look? Well, this actually looks quite stable with time, which is nice. Okay, so one final thing here then is you can use these results as a sanity check for the way that you've set up your simulation. So things to check, yes, our pressures match here. What about our mass flow rates? Now we used a given ratio of mass flow rate, I believe it was 66 kilos total for flow line B and 27 kilos per second for flow line A. Does that still add up in our new combined simulation? And if it doesn't, that might indicate that you want to go back and slightly tweak the way that you've built your blended file so that it actually matches this combined result. Okay, so that's basically the end of our tutorial 3, where what we've done is to go from a relatively simple case here, where we had a mass flow rate as our inlet condition. We've then made it much more complicated by changing our boundary condition type and adding in a second production well. And we've seen how we can blend these fluids together and actually sanity check those results. So, In tutorial 4, what we're going to be doing is moving from these complex steady-state cases to transient cases. And we'll start by taking a look at shutdown and restart in OLGA.